recording. Okay, so yeah, Dresden Files, awesome book series. Read it if you haven't. If you need more stuff to read during the if you're a big fan of this is urban fantasy, so basically fantasy but taking place in modern day stuff. If you're more into more traditional fantasy, big worlds and that kind of stuff, Wheel of Time, very awesome book series, and the King Killer Chronicles. This one's been completed. This one we're still waiting on book 3. It's going to be out some point, possibly this year. But this is very awesome. Okay, so anyway, what we're going to go over today is that we are going to do review for the final exam. Okay, so the way I'm going to do this is, rather than having a practice exam, is that I have the study guide under my... So, I look, creating a lot of practice exam for the final, I have only so many good questions to ask during the final, and I don't want to use them all up. So, what I do is that over here, right, you can find this in my GitHub, go to the data structures folder, go to study guide, click this so that you actually download it, because you can't click the links, the embedded links, unless it's actually in like a PDF reader. So I'm going to go and use, not the first one, not the second one, this third link over here to begin with, which is the Harvard Practice Final for Data Structures. It's a very good practice final. And we're just going to go through as best we can. Let me hook up my... I'm going to go and hook up this... my Wacom tablet so that I can write stuff and annotate on the screen, because if I was totally prepared I would have done that, but I forget that I unplug it occasionally because I'm awesome like that. Okay, so this is and basically for the next couple days what my plan is I'm just going to review these things, because these questions are really good and they really cover the kind of stuff that it's going to be on the final. When is the final? I think it's Friday. I think it's not this Friday, but the Friday after, at 3:30. I have to write it for everybody. That's going to be doing, so everybody's going to be getting the same final, but that's what's going to be going on. Basically once I'm not working with you guys. So, day and time is, I think it's next Friday at 3:30. I will send out a full email announcement. If for some reason you find out you can't take it, like at the appropriate time, here's the rules. Email me at some point before the final. You don't care if it's even like 5 minutes before the final. Just email me. And if it's before the final, and you're telling me, Professor Rosen, I did not sleep all night because my brother was a jerk and decided to, decided that coming into my room to play the trumpet at 2:00 in the morning was a great idea. So, because I'm sure some of you are home and you have annoying younger siblings, or possibly annoying older siblings, or possibly annoying twins, so... so long as you let me know, like, before the final exam that you need to reschedule, we can reschedule. I'm very flexible. Okay? So, let's go ahead and work on this final exam. Let me zoom in so that we can actually read. So, the way their practice final works is that basically they give you the option of... This guy is, like, super exact, and he says you should budget 1 minute per point. So, meh. Specify up to 2 answers. Your first choice should be written. So basically, and then if you want a second choice, you'll get 1 point for your second. If your first choice is wrong, but your second choice is correct, which is really a good way of doing multiple choice, in my opinion. So let's go through this. Now, I will say that they did not that the person who wrote this is pretty awesome, but not awesome enough to have used LaTeX. So, points off for that. So let's go ahead and take a look at this. Suppose that items A, B, C, and D are pushed in that order onto an initially empty stack. The stack is then popped 4 times, and as each item is popped off, it is inserted into an initially empty queue. If we remove 2 items from the queue, what is the next item to be removed from the queue? And if you're trying to do this in your head, stop, because I'm not going to do it in my head. That's vexing. So let's go ahead and put everything into a stack, right? Let's go ahead and say, so let's put A, B, C, D, and E, right? This popped into an initially empty stack. And now pushed into an empty stack. So E is at the top of the stack, A is at the bottom. I like to do my stacks vertically. And now, as each item is popped off, it is inserted into an initially empty queue. I'm just going to write it from this way, with this being the front of the queue, this being the back of the queue. So 2 items removed from... So let's go ahead and pop it 4 times. E, D, C, B, right? Now we remove 2 items from the queue. Well, we always remove the first items, so remove 2 items from the queue. What is the next item to be removed? That would be the item at the front, which is item C. So the answer for this is C. And clear all drawings. And now go back to mouse. Alright. If the binary tree below is printed in pre-order traversal, what would the result be? Okay, so pre-order is let me handle myself. So let me handle myself first, then I'm going to handle my children, right? Pre-order means myself, then my children. Me, left, right. So post-order is left, right, child. Sorry, left, right, myself. And in order is left, myself, right. Everything that's less than me, me, and then everything that's greater than me. So pre-order, so we know basically just by looking at this sucker that A cannot be correct. And B cannot, that looks terrible. So let's just do A and B cannot be correct because those basically are looking at basically doing the left subtree first. Also notice this is a binary tree and not a binary search tree, right? Right? So it's not a binary search tree because it's not we've not got stuff in order. So let's do a pre-order traversal. Okay? So we're going to do myself, 6. Then we're going to do my left subtree, which will do itself, then its left subtree, then so 6, 17, 9, 4. So it looks like this one's probably going to be correct. So let's go ahead and check the next part. So we did 6, then we did 17, then we did 9, then we did 4. Now we do the right subtree, 22, 16, 12, which is what's going on in E. So the answer here is E. Make sense to everybody? What I did is I said, let's do 6, then we're going to pre-order the left subtree. And doing the left subtree said, let's do 17, and then let's do this left subtree, 9. And then when we were done with 9, we said, okay, we did myself, we did my left subtree, now let's do 17's right subtree, which was 4. So that's why we did the pre-order traversal there. Does that make sense for everybody? Okay, cool. Cool. All right, next question. Clear. All right, next question. I love this question. A graph implementation that uses a 2-dimensional array to represent the edges would be most reasonable for which of the following cases? And let's just say A, B, C, D, E, and then it says none, since a graph can only be represented by a linked structure. Now, if you watched the videos and read the book, you should know that basically there are actually 2 ways to represent a graph. You've got your adjacency list, which you could also implement using a map. But that's a linked structure. Basically, we basically have a list of lists. And basically say, hey, or a map of lists and says, hey, this guy is linked to all these other guys. And the other way is an adjacency matrix. So one way is saying for each node, here are the edges that I have. And the other is saying for every edge combination, here are all the possible things we have. So let's see. Now before we go on into our answer, I do want to examine them all. Now I did say, so the question is, when do we want to use these? And the answer is that we want to use a linked structure for a sparse graph. We want to use an adjacency list when it's sparse, and a 2D array when it's dense. And the standard that our book uses is that it's dense when 25% of all possible edges exist. Now, how many possible edges are there? Well, if we have n nodes, right, then the number of possible edges is n squared, right? Because we can, in a simple graph, meaning that we can have one edge, between pair of nodes. Each node can have up to one edge between each other node. So A can go to A can go to B, A can go to C, A can go to D, and so on and so forth. And then we can also treat edges, and then if it's directed, right, B can go to A, B can go to B, B can go to C, right, and so on and so forth. So let's go ahead and take a look. We have 1,000 nodes here and 1,200 edges. So 1,000 times 1,000 is 1,000,000, right? So 1,200 out of 1,000,000. This is a sparse node. This is sparse, right? That's basically, not much of that. That's like 0.1% over here of possible nodes. That's not 25%. We've got 100 nodes, 4,000 edges. So that means that 100 squared gives us 10,000. So 4,000 edges out of a possible 10,000, that's 40%. That seems really reasonable. 1,000 nodes, 10,000 edges. So 10,000 out of 1,000,000. That's, again, 1% usage over here. And then 10 nodes, 20 edges. Is this sparse or dense? Well, 10 squared is 100. So here we are using 20% of all possible edges. Here we're using 40% of all possible edges. So it's most reasonable to use it for this case. Does that make sense to everybody? Everybody was following that about the adjacency edges and adjacency matrices? So do we need to know why a linked structure is better for sparse? And if so, can you give a TLDR? I don't think you need to know why. I mean, that's probably a good question to ask, but here's the reason why. With an adjacency matrix, right, you've got all of these possible combinations over here. And so, if basically we've got all these combinations, and basically, we're making this 2D array. And if we're going to be filling with this 2D array with a bunch of nulls, because it's a sparse graph, then that's going to be pretty wasteful, right? Right? It has something in that entry if there's an edge there, and if there's not edge there, it's a null or some other kind of empty stuff, and so that's just a lot of missing information. The question is that memory overhead? At what point is that memory overhead not exactly wasteful? And that's in a dense graph, and the book says that's around 25% of all possible edges existing. Because remember, using a map or a linked list or whatever other structure we would use for an adjacency list does have the associated overhead with, it does have an associated overhead. All right. Oh, I like this question. It's also the type of question that I always hated to get as a student. But I like this question specifically, but I've always hated this kind of format. Which of the clauses is correct? Beautifully explained. I didn't think I explained it that great, but okay. So binary tree is constructed of nodes that are instances of the following class. So here we just simply have given a node with an integer, and then we've got this static method for a binary tree, which is mystery root, and says, hey, if the right node is null, return myself. Otherwise, return mystery on my right node. You consult 3 supposedly tech-savvy consultants and get the following 3 opinions about what the method does when passed a reference to the root node of a binary tree. You get the last node visited by in-order traversal, the last node visited by a post-order traversal, and the last node visited by a level order traversal. So which of these is correct regardless of the way the tree works? So let's go through this. So mystery, what will mystery return? Mystery is always going to return, if we examine it for a bit, it's always going to return the rightmost node. In a binary search tree, it would return the biggest item. Why? Because, hey, let's start the root. Doesn't really matter what we have over here. Right? It doesn't really matter what we have over there. Right? If we pass we pass root into mystery, is root.right equal to null? No, it's not. So we call mystery on this one. Is root.right equal to no? No, it's not. So call it on this one. Is root.right equal to no? No, it's not. Call it on this guy. Root.right equal to null? Yes, it is. So I return myself, which this guy returns him, this guy returns him, and this guy, again, returns this all the way back up. So it returns this guy. Okay? It so happens that this would be the last node in an in-order traversal, right? In-order says, let me do my left subtree, then myself, then my right subtree. And this guy always is the right subtree, right? Let's think about this for a second from his perspective, right? If he had a right node, it would return this guy. So, and it wouldn't return him. If it was in this situation, right, where he's got a left subtree, he'll do his left subtree first, then himself. So, 1 is true. What about the last node visited by a post-order traversal? Well, we've already written a counter case over here. The last node in a post-order traversal is the root itself, this guy. Right? So, we'd be returning this guy. So 2 has to be false. Now, the last node in a level order traversal. What in the world is level order? That's something. So that's actually something. Now, you might think we've not gone. Whoa. Stop. Now, you might think that we've not gone over a level order traversal. And that's true. We haven't gone over it directly, but you just learned what it was. Level order traversal is breadth first search. Basically, level order traversal is, and I'll just simply label everything like this. So this node, then this node, then this node, then this guy, this guy, this guy, this guy. Don't really learn it during the tree method, the tree stuff, because it's not done recursively. You got to use a queue for it, right? It's breadth first. All trees are graphs. Okay, all trees are graphs, and so this is just simply a breadth first search through this graph. Okay, so level order. So it does kind of look like that we would be the last node in a level order traversal, unless, of course, we create a counter case. Right? So let's go ahead and make a counter case. So mystery returns 3 now, but it would not be the last node in a level order traversal. The last node in this level order traversal would be 5. So, I keep clicking on the wrong, like these little hanging things on my pen, so that's why. So the answer's got to be A, 1 only. I appreciate the compliments. All right. With a poorly chosen hash function, it is possible to have a situation in which the search time in a hash table then goes to what? So, if it's poor, ideally, so let's take a look at this. Ideally, this is what we want. So that's got to be wrong, because when it works well, it's constant time. Next. Login doesn't seem that bad, so no. It's probably O of n because, right, with a poorly chosen hash function... Oh, let me actually write a very poorly chosen hash function right now. That seems like a good idea to do when it's asking you, what is a poorly chosen hash function? Let me write my hash function to be h of x, where x is my key, is equal to 0. Okay? So that's a hash function. It's a legit hash function. It's a terrible hash function, right? What does this do? It maps every index. It maps every key to index 0. Guaranteed to work in any. This is guaranteed to work in any hash table in any hash table. But basically, if we're using a hash table with chaining, this is going to mean that everything's in the same bucket. If we're using open addressing, this means we're going to get a collision each time. So that basically means if we're using open addressing, we're going to go from, we're going to hit here, and then we're going to look to put. So if this spot is taken, then we're going to go to the next spot. Then these 2 spots are taken, so we're going to go to the next spot. Then these 3 spots are taken, so we're going to go to the next spot, which means that this first one took 1 time, then this 2, then this 3, then this 4. So, yeah, that's O of n. O of n factorial, if you manage to write it that way, I think that's like some kind of accomplishment or something. That seems really special to get it that bad. And finally, n squared, I don't think, again, really as bad with the search time. Maybe it's possible to have it with like a quadratic, with like the open addressing with quadratic search, but to get it to n squared or n factorial. But honestly, most of the time with a poorly chosen hash function, specifically the one I gave you, you're going to get O of n time. That's really what we're looking at. Clear all. Yeah. Hey, you recognize this? This question, this is totally where I got the question from the first exam from. So I'm going to skip it because it's not going to be on the final. But basically, it's the which of these is, just going forward and back and forward and back. I like this one, though. Let's continue on with hashing functions and stuff. All right. A police department wants to maintain a database of 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not a given license plate number is in the database. Speed of response is very important. Efficient use of memory is also important, but not as important as speed of response. So which of the following data structures is most appropriate for this task? So in other words, we want basically the better O of n for the best big O for our speed. And memory efficiency, yeah, we want to be, if there's multiple things that are the same speed, we'd want the more efficient one. That's the way I'm interpreting this. So let's go ahead and look through this. A sorted linked list. So a sorted linked list, how long does it take to find something in a sorted linked list? Any takers? A sorted linked list, how long that's going to take? O of n, says Brian, and that is correct. It takes O of n. The linked list being sorted does absolutely bloody nothing for us. Because to find anything in a linked list, you have to iterate through the linked list. There's no way to kind of go into the middle and do a binary search over a linked list. So this is O of n, which is no bueno. And also it's going to be O of n space, right? They're all going to be O of n space, to be honest. It's just a matter of how much extra we're going to use. So a sorted array with 1,800 entries. So if it's sorted, how much space, if it's a sorted array or a sorted array list, how much, what's the big O for this guy? If it's sorted. If it's sorted in an array, well, if it's sorted in an array, we can use binary search on it, right? If it's sorted, yeah. O of log n, right? Because we can do binary search on this sucker. O of LG n. And just kind of a notation thing, just like one of the things that I use a lot is log n. We can kind of assume that log is base 10. And we all know that ln is like log of e, right? One thing I see a lot in computer science is using LG to represent a log of base 2, which kind of makes sense. 2 letters, so it's base 2. Nice reminder there. But the cool thing is that when we are talking about log time in big O notation, log base 2 is the same as log of natural log, as same as log base 10 in terms of ranking big O. They're all logarithmic time. But for the answer for the thing on the previous exam, it was the thing was it was going to run slightly faster because you had 3 branches, which meant that it was a log base 3 of n steps for that last question on the previous exam. So anyway, going on, this is log base m, which is better than the sorted array list. And as far as the space is going, the space is pretty good, right? You're using exactly as much space as items you have with no overhead, essentially. Right, with the linked list, we have the overhead of going forward and back. So this beats it in both regards. Now we have 3 hash tables. They all use open addressing, okay? And we have 1,800 entries, 3,600 entries, and 10,000 entries. Okay, so really the speed really depends on, and a lot of this, and now when we use open addressing, and we're trying to rank the speed, the best way I've found to think about these things is looking for a parking space in a parking garage, right? So suppose we have 1,800 parking spots in this parking garage, and 1,799 of them are full, right? Now we know that this guy is only going to ever have 18. We know for all these parking decks that 1,800. There's only going to ever be 1,800 cars in them at once. But if you're the last parking car going into the parking garage here, which has a capacity of 1,800, then how long does it take to find the last space in a parking deck? It takes freaking forever, right? You enter the parking deck, you see it's full. You go, okay, I'm going to go up. Oh, it looks like a space. Okay, going up. Oh, no, it's a smart car, and it just looked like an empty space, and it's not. So now I have to back out of that turn I was making and go up. Oh, there's another empty space. No, wait, it's a motorcycle stuffed in between 2 cars. Okay, gotta pull out. Oh, that looks like an empty space. No, it's reserved, right? If the parking deck is pretty much full and you're looking for that at last space, it takes freaking forever to do. Okay. It's like I've done this before. Okay, speaking from personal experience here. However, and we see this basically and this is basically saying, right, we've got a hash table with 1,800 entries and 1,800 space. It's going to take O of n basically to find something because there's going to be so many collisions, right? The more spaces we have, the less collisions we're going to get. So this takes O of n time, essentially, because we don't have enough spare space, right? One of the big things about hash tables is the speed up happens because we have a bunch of empty space, right? There was a formula in the slides that we could use that Knuth came up with. Now with a hash table with open addressing and 3,600 entries, that's 50% full at most. So that's actually a really good runtime because we're looking on an average of, if we use the formula. So let's go ahead and just let me Google it for a second. Mouse Knuth's formula hash open addressing, right? And this with linear probing. Right, so this is the expected search, which basically is, and that's Sedgwick over there. That is their source, but I know that Knuth, basically, that our book cites Knuth. It's the same thing. Yep. See here. So there's Knut's summary over there. But the point being is that basically, if we plug this into our this with our maximum load factor, our maximum load factor is 0.5 here. Okay, so 0.5 is 1 plus 1, so 1 over 1/2. What is 1 over 1/2? 1 over 1/2 is 2, that's right. So plus 3. So we're looking at the worst case scenario, like 3 expected on average. Not too bad. It's actually a really... So we're looking pretty good over here for it's half full, right? If it is half full, it takes almost no time at all to find an empty space. So this guy over here is probably our best bet. But let's look at the last guy. The last guy is open addressing with 10,000 entries. Super fast. Super fast. But really, is the extra space being used here worth it when we're already super fast over here? So I would go with D. I would argue D because, you know, this is using half of the space in the hash table gets you really fast. And over here, we're just burning space. We're just burning space unnecessarily. So I would go with D because D has constant time and we're only using basically O of N extra space. We're using N extra space specifically. And here we'd be using at least like, I don't know, like 3N, 4N extra space? Close? Yeah, close to 4N extra space. Alright, so we didn't do Huffman trees on the previous exam. But... So I'm going to do something fairly straightforward on this exam because something more along the lines of this on this exam, I think. So a Huffman tree is constructed from a text document containing the 5 characters. The character E appears the most frequently, and the character I is the next highest frequency. Which of the following could be a Huffman tree for the document? I'm right, I didn't have Huffman trees on the exam, and if there's something that's going to be cut from the exam, it's going to be Huffman trees because... Huffman trees are just... It's just... Again, that is the one concession I might be making for this semester. As much as I like them. Okay. So, which of the following could be a Huffman tree for this document? E and I are the highest frequency. So they appear the most frequent in this document. So first off, 1 is not a Huffman tree. It violates one of the fundamental rules of Huffman trees. Huffman trees... all the nodes have to be at the bottom. All the nodes have to be leaves. So over here, now, and the other thing is the more frequent node should be closer to the top. So number 2, E is pretty close to the top, and I is at the bottom, but that's possible. Like, if this guy's frequency, if the frequency of this tree is like, you know, E has a frequency of like 100,000, and this guy has like a frequency of 1,000 and 10,000 and 5,000 and 1 and 1, then this is a possible this tree will, you'd get this tree if this was the weights of each of these items, right? 1 and 1 would go together, create a new tree. Actually, it would be 1 and 1. I'd have to. It's annoying. I'd actually have to work this out, but it's possible that we could have some X and Y such that if they were added together, they'd be greater than 15,000. But less than these guys. So I'd have to adjust these guys in such a way. But it's possible to end up with this tree. Okay. On the other hand, 3... these I and E's are closer to the bottom. Or, you know, I and E are supposed to be the most frequent, so they should be closer to the top. So that won't work. So the answer is going to be 2, I noticed that none of these is an answer, so let's go ahead and create an example of this. So let's actually work out. So using some crazy number up here, this will ensure that this guy is up here by himself. And we'll see that as I construct the tree. So let's go ahead with 1 is not a good answer because because I and T are internal nodes. In Huffman trees, all the actual items have to be, all the things that you're counting the frequencies of have to be external nodes. Okay, let's go ahead and say 5 and 6 will give us 11. And then let's go with 5 and 20. That will give us 25. And let's go with 7 and 8. 5 and 20. I'm trying to come up with something that basically... So this guy plus this guy has to be less than this sum. But its sum has to be greater than both of these items. So T and O have to be... Let's actually work this out. T plus O has to be greater than S plus I. And we know that also that T is less than O, less than S, and that's less than I is the issue. And we also know that T plus O has to be greater than... Sorry, T plus O has to be less than S plus I. We also know that S is less than I, which is less than T plus O. That is the inequality that is trying to be solved here. Does that make sense to everybody as to why this has to be the case? Please, I'm using that to basically establish whether or not this should be on the exam or not. Okay. So that last inequality, so we know that S plus, so here basically we know that the way this had to resolve is that T and O have to be, so we know that basically that T and O have to be together because they're going to be the first two things in, basically we are going to create a priority queue. T, O, S, I, E. Okay? We know that if we add T and O together, that what's going to happen is that they're going to get added into a single node, which has a combined weight that will be greater than S and I, because S and I get joined together. So basically T and O would get lower in the, would get moved back in the priority queue because it would have a higher weight. So S plus I then would get added together. And then since we know that T and O is on the left, but also we know that E has to be less than the combined weight of this guy. It's actually rather annoying to figure this out. And I'm sure that basically what I'm instinctively thinking is that I'm sure that there's a solution for this. But I also know that basically that it is probably not a worthwhile thing to try to figure it out. So I would go with B, and my second choice would be none of these. Because basically, I mean, actually, hold on a second. Yeah. That will do it. 1, 10, 20, 30, 40, And then... Actually, no. Sorry. 11, 12, 13, 14, and then 30. That'll do it. That will basically make it go that way. Because T and O will get added together. The combined weight is going to be 23, which is greater than those two. 13 plus 14 are going to get added together. The combined weight is greater than 11 plus 12, so they're going to go after in the queue. Does that make sense to everybody? And then finally, this tree's combined weight is, is greater than 40. Great that you all watched the videos. Awesome. So maybe something I might do for this is basically come up with these and basically ask you to come up with weights for it. That might work. That seems like a good idea. All right. An array of 7 integers. Sorry for burning some time on that, but I wasn't sure how many students had totally... The final answer was B. 2 only. So, this covers heap sort, but the big algorithms for sorting we especially care about quick sort and merge sort. So, an array of 7 integers is being constructed by the heap sort algorithm. After the initial phase of the algorithm, which is building our heap, which of the following is a possible ordering for the array? So, first off, when we do heap sort, we create a max heap. So, D is incorrect because the biggest item has to be there. So, really what we're doing is making sure which of these is a max heap. So, what we can do is so one thing we can do is that we can draw these out, like with this first one. 45, 51, 53, 47, 49, and ask ourselves, hey, okay, sorry. I had one last question about this last problem over here. This one is wrong, not because it's got an intuition, but because the only way to get these guys at the bottom like this, to get at a lower level, right? These guys would require 3 bits to basically encode, right? But this guy would require 2 bits, 2 bits, and 2 bits, which means that these guys would be more frequent. So the only way that will happen is that these guys have lower frequencies. And the problem setup said I and E have the highest frequencies. So that's why. Okay. There we go. So, erasers. And don't worry, basically the next 3 lectures are going to be all me doing this stuff. Reviews. And okay. So, we know from this that basically we can see at this tree that we do not have that the max heap property is violated here. 45 is less than 47 and 49. Remember, these are complete trees, so you can just kind of order them left to right. So A is incorrect because this violates the max heap property. Right? 45 is less than 47 and 49. The biggest item should be of a heap or subheap should be the root, so that's not true there, so this isn't the appropriate max heap. The other way we can do that is just to remember that that formula that you can use and say to ourselves, hey, well, 85's children are 49 and 78. Great. 49's children are 45 and 47. Awesome. It's bigger than those. 78 is bigger than 51 and 53. That seems kosher. So let's go ahead and check this guy out. 85 is greater than 78 and 49. 78 is greater than these two. 49 is less than those guys, so C would be wrong. Already established D is wrong. And 85 is greater than those two. 51 is Greater than 49, but less than 53. So, violates that one. The answer here has to be B.
Is heap sort always going to use a max heap?
Pretty much, yeah.
Okay.
It will use a max heap, and then it's going to sort that max heap by removing an item. If you wanted to get if you wanted to get it so that it was sorted from the greatest item to the least item, so you wanted to reverse sort it, you would use a min heap.
Gotcha.
Okay. So, this question also was like what I used on exam 2, which is, here's a tree. Which of these guys is going to create this tree? Which I thought was a really good question for one that I could auto-grade. Hi, Molly. My cat is basically being very friendly right now. So, 5. So, basically, let's look through this. No need to reproduce this. 5, 3, 4, 9, 12, 7, 8, 6, 20. A is perfectly fine. We're looking for the one that will not produce the binary search tree. So, rather than using a check, which might get confusing, or an X, I'll just put a dash there. That's perfect. That's fine. No comment. 5, 9, 3, 7, 6, 8, 4. So that was fine because we did the 3 before that. What we're looking for is kind of a gap. Something, a creation that would put in a gap, because you can build this tree in a whole bunch of ways. Now we do 12. 12 came after the 9, so that's perfectly kosher. And the 20 came after the 12, so boom. Okay, that's perfectly fine. 5, 9, 7, 8, 6, 12, 20, and then 3, 4. 5, 9, 7, 5, 9, 7, 3, 5, 9, 7, 3, 9, 7, 3, 8, 5, 9, 7, 3, 8, 12, 20. Sorry, my 12. I missed the. I jumped from. I missed reading line. 12, 6, 4, 20. Yeah, that's the hardest part about this. Your eyes might glaze and you might jump from one line to another. So 5, be sure to do them all, even if you think you had the right one. So 5, 9, 3, 6, 7. 5, 9, 6, 7. So the answer is E over here. Because basically if we were to build this one, it would be 5, then 9, then 3, then 6, then 7, then 8, 4, then 12, and 20. And this looks very different from this one, and not just because my handwriting is terrible. Alright, answer 3 of the 4 questions in the space provided. Now this is... So what I recommend is actually, if besides the exams, go ahead and look for a ton of other data structures practice exam. But you'll find that there's things that other classes go over that we don't. This is because a lot of things get combined into data structures and algorithms and stuff. And it really just depends on where we prioritize our stuff. And we do a very broad stuff. As our curriculum goes through, we might find that we have more time for doing stuff like a 2-3 tree. If we can definitely get array lists more covered in 1068, but that really just depends on a lot of stuff. We want to make the right balance of basically making sure we can cater to as many students as possible without like breaking anybody. So suppose the keys in the middle row of a standard keyboard is American standard keyboard, ASDF, GH, HJ, KL, are used, and this is an QWERTY keyboard, are inserted in succession into an initially empty binary search tree. Draw this tree after the sequence of insertions has been made. Alright? A, S. So S comes after A. D comes before S. A, S, D, F, G, H, A, B, C, D, E, F, G, H, I, J, K, L. A very unbalanced tree, but a very easy 7 points. There. Now here what they're saying is do the same thing but for a 2-3 tree, which is one of the types of self-balancing trees, and it has a tendency to split. But anyway, this is much more of the style of what you can expect on the exam. Here we go. Hashing. You are given an empty hash table of size 7 that uses open addressing. The following sequence of keys to be inserted is 15, 17, 8, 23, 3, 5. I guarantee you will get something that's similar to this on the exam. We give you a bunch of items. We give you a hash table, and we tell you, please give us the answer. Insert these keys using the following approaches. If an overflow occurs, say so and indicate which element causes the overflow. And I'm going to just try to do this in a way that will be as easy to autograde as possible. So keep that in mind when I write this. So I might not be caring about the overflow so much, or I might have that as a separate question. Or something like that. So I'll be doing a lot of drawing here. Oh, and on the final exam, I will of course have a file upload as the last question. I say of course, but I didn't do it last time. What I'm going to do is I'm going to have a file upload as the last question, where if you have any notes or any work or anything else that you want to kind of submit as you're doing it, like basically just to show us, hey, this is my, here's my work for this problem or something like that, and you just want to make sure that you could possibly get extra, some partial credit on a question, there will be a place for you to submit files. So if you need to take a picture or something and submit it there, then that's fine. Okay. So 15, 17, 23, 5, 3, and 5. These are the keys for the items we want to insert. We don't care about the items themselves. We just care about the keys. So here's the approaches we're going to be using. Our hash function is xmod 7, and we're going to do linear probing. Honestly, the hardest part about this for some students was doing the modular arithmetic, but you have access to a calculator, so, and your electronics, so that won't be too much of an issue. So 15 mod 7 gives us... so which index will this go? Right? Doing this hash function of this mod this tells us where it's going to go in the table. So 15 mod 7 is 1. So 15 is going to go here. Right? 17 mod 7. Right? Mod 7. So we can go up to 14. 17 minus 14 is 3. 8 mod 7. 8 minus 7 is 1, so that gives us that we want to put an 8 here, but we can't. So what we do is that we take that 8, there's a collision, and we look for the next available space. So we put the 8 there. Make sense? Next, 23. 23 mod 7 is, well, we can subtract 7, then 7, then 7 for a grand total of subtracting 21 from this. So 23 minus 21 gives us 22. 23 minus 21 gives us 2. So we can put it. So we want to put this here, but we can't because it's taken. So we'll put it in the next spot, but we can't. So that's taken. So we're going to put it over here. Make sense? Okay. 3 mod 7 goes to index 3. Remember, so basically, x mod y yields x when x is greater than, got my inequality wrong. When x is less than y. Just remember that. That's a very easy that's a very easy bit of modular arithmetic there. So, just important to remember. 3 mod 7 gives us 3, so we want to go put it 3 in index 3, but we can't because 17 is there, so we'll go to index 4, but we can't because 23 is there, so we'll go into index 5. So 3 goes here, and now 5 wants to go where 3 is, but it can't because, right, I just said. So we put it there. All right, next guy. Next guy is that we can do X mod 7, but we're going to use quadratic probing. So the first steps are going to be exactly the same. 15 goes here, 17 goes here, right? And now we do 8 mod 7, which gives us 1, and we want to go here. So the next step is, okay, can't go here, so we're going to look 1 squared away. Now 23 wants to go into index 2, but it can't. So it's going to look 1 squared away. Okay, but it can't go there because that's taken. So we're going to look 2 squared away from our original space. So 1, 2, 3, 4. Okay, 23. 3 will go here, and then 5 just simply slides into there. That makes sense for quadratic probing? Quadratic probing is the next available space, where the next available space is defined as 1 away, then 4 away from the original space, then 9 away, and then 16 away. Right? 1 squared, 2 squared steps, 3 squared steps, 4 squared steps. Whereas what we were doing for linear probing was, it was 1 away, 2 away, 3 away, 4 away, which was, of course, 1 to the 1, 2 to the 1, 3 to the 1, and 4 to the 1. That's how far away those things were. Okay. There's no real need to go over the double hashing portion of that because we didn't really cover that. But basically that means, hey, if the first hash function doesn't work, because what this says, hey, if there's a collision with our items, then use the second hash function to figure out what space to go to. Okay. Graph algorithms. Right? It's all about just doing whoever does a different focus on different things. So, graph algorithms. Perform a depth-first traversal of the graph above. Starting at vertex C, select the smallest edge visited when appropriate. In the space above, list the vertices in the order they were visited. Okay. Sorry, in the space below, list the order that was visited. Okay. So I'm going to create a set over here called scene. Okay. So first thing is that we're going to start with vertex C. Select the smallest edge. So in other words, right, C, with depth first search, what I'm going to do is that I am going to do, and I'm going to create my stack over here. So C is in my stack. And what I can do is that I can go either to B, to E, or F, right? I can select one of these three edges to travel down. But the smallest edge is what I should select first. So that means go to B. Make sense? So push B onto the stack. And I'll go to B next. Okay? Next, I'm currently at B because B is at the top of my stack. In fact, I can create my stack over here on the side. C, B. B is at the top of my stack. So let's go ahead and see where I should go next. So I can go to C, but I've seen it. B could go to F, E, D, or A. A is the smallest, and I haven't seen it yet, so A goes onto the top of the stack to represent my current location. And now I'm currently at A. And another thing you can do is that if you were working on paper is that you could totally just like mark this guy and mark this guy to count them to just give yourself a visual reminder that you've seen these guys. Or rather, this probably gets a better name with visited because, yeah, visited. So now I'm at A. So, A can go to B, which has been visited already, so that's no good. And D, I could go to D, which hasn't. Well, that's my only valid choice, so I'm going to go to D. Okay. So now I'm at D, and I could go to B or A, but I've visited both of them, so I'm going to pop off D. Okay, now I'm at A. A can go to B or D, but I visited both of them, so I'm going to pop off A. So now I'm back at B, because how do I know where I'm at? Top of my stack. Now I'm at B, and I have 2 valid places to go. Right, I can go to F or E, and always go to the smallest edge, F. So go over here. And then 30 and 18, but they're both visited, so we're going to pop off F. Okay. And now we're back at B. We've got only one valid choice to go to, so that's E. Go to E. Can't do anything, right? Can't do anything there, so we pop off E. We then are back to B. Can't go anywhere, so we pop off B. And to backtrack, then we're finally at C. Can't go anywhere, so we pop off C. Stack is empty, so we're done. Return visited. And so we go to C, B, A, D. Backtrack all the way to B, then F and E. And that's a depth first search. Right? Think about the... if you think about it, it kind of just creates ourselves this nice tree for us. Right? Using this... using this edge... Right? And you can see basically that we go kind of as deep as we can before we do anything else. Okay. Next, perform a depth first search. Can you guess what's going to come next after this one, by the way? Any takers? If you guess Dijkstra, then you're absolutely totally correct, and you figured it, and you know how learning about graphs works. Always a Dijkstra's question on any exam that you've learned about graphing. So once we're done with these, I don't want to go over time, but at the same time, I'm going to definitely get through the Dijkstra's question, and I can guarantee that Dijkstra's will be at least worth 8 points. Okay. So next, we've got ourselves breadth first search, starting with C. Same thing. Select the smallest edge. So let's go ahead and say this is our Q, and this is well, actually it's fairly straightforward. We're going to start at C, right? So we start at C. Again, I clicked on the thingy on my pen. So we're going to start at C. Then we're going to do, then we select then next what we're going to do is we're going to go to B next. And then we're going to go to, after B, we're going to travel to E and then F, because they are the cheapest in that order. B has 5, to get to B is 5, to get to C to E is 22, to get to C to F is 30. So that's the order in which I'm going to go to them. Next is going to B. From B, so from B, I don't need to mark anything. From B, I can get to A, D, E, and F. So what order am I going to go in now? So A, so C to E is the cheapest. B to C is the cheapest, but I've already seen it, so never mind. So, E and F should be in here because I want to make sure I'm not seeing them, or I'm not re-adding them. So, F and E I'm not going to bother dealing with because they're already in the queue. Next would be A and D. So, I'll go to A and then D next. And then that's it. So it would be E, F, A, D, right? There's only 6 nodes. So C would go B, E, F, and then we would go to A and D after that, because those are the cheapest. breadth first search is really easy, right? We visit our neighbors, then we visit the neighbors, and then we visit the neighbors of the neighbors of the neighbors. Generally advisable to have 3 sets, right? One for visited stuff, one for stuff we still have to go to, and the like. So here, Dijkstra, I'm going to use this space over here, up here for Dijkstra's. Suppose we have Dijkstra's algorithm, find the shortest path from D to vertex E. So to find the shortest path from D to E, we have to find the shortest path from everything else. List in order in which they become known, all the vertices which the shortest path is determined, and the length of the shortest path. So what we're going to do is that we're going to just create our set over here, A, B, C, D, E, F. Right, we're going to go ahead and just do full Dijkstra's. So we're going to start with, so we have our D, which is our distance, and P for our previous. Okay, and so what we're going to say is that so we're starting at node D. The setup is to start with node D, and then E is, everything has a distance of infinity to start out with. Okay, and then everything I can get to any other node for an infinite cost from D. Okay, so now D has 2 neighbors. So first we go through and we select the node with the cheapest cost. Having not infinity is the cheapest cost. So D is what we're going to select. So 10, 17. So I can get from D to A with a cost of 0 plus 10. If that's cheaper than what we currently have, yes it is. It's cheaper than infinity. So now we can say, hey, we can get there to A for a cost of 10 from D. Similarly, to get to B, we can get there from D with a cost of 17. Sorry, I was listening to the conversation my wife and kid were having. So, there. So, now we go through. Which of these is the cheapest? 10, 17, infinity, infinity, or infinity? Well, 10 is, so that's going to be the next node. So, what we can do is that we can get from... So, what new information does this give us? Well, we can get from A to B with a cost of 13 plus 10. 13 plus 10, because that's how much it costs to get to A to begin with, and then we can get to B for an additional 13. So is 23 less than 17? No, it is not, so we don't update anything. Next. So now let's go through. Which is the cheapest, 17 or 3 infinities? 17 is. So now 17 we can get to... So we can get from B to C with a cost of 17 plus 5. So that's 23. Is that cheaper than infinity? Yes, it is. So what we do is that we say, hey, we can get here from B for a grand total of the 5 that took to go from B to C and the 17 that it took to get to B. So 23. And do the similar for E, which would be 37. And I'll do more Dijkstra's examples and graphing examples and when we go over other exams. Okay, so both of these go from B. So E and F. So 37 for E. And then 35 for F. So next, select the cheapest one of these. That'd be 23. Does 23 plus 22 give us anything better? No. Does 23 plus 30 give us anything better? No. Next, select the cheapest, F. Does 35 to... Does 35 to... Actually, there's... Everything else leads back to things we've already seen, so that this adds no new information. Finally, E. We're done with E, because E provides no new information. So we're done. So this is our graph. So list in the order which they become known all vertices to which a shortest path is determined in the process of solving this problem. So what is the order that they would become known? The order they would become known in this order: D, A, B, C, F, E. In other words, they'd be known in their order of the shortest path. Make sense to everybody? Dijkstra's is not a particularly hard algorithm. It is also a famous algorithm. If you are having trouble with Dijkstra's and going through it, there are tons of examples online for you to catch. Alright, so I am done with the review for today. I'm going to be working on creating the exam and over the next couple of next day or two. That will give us a more accurate picture of what needs to be covered. I'm also going to post this online. If you need to, I'm going to go ahead and stop recording. If you need to speak to me, please send me a private message and I'll stay behind. And then we can set up breakout rooms so I can speak to you accordingly.